Hey class, it's Mr. M with another assessment question to look at. Here we're being asked to find and classify local or relative maxima or minima, or extrema, and we're being asked to justify our answer. Notice there's no interval in question here because local or relative extremas occur in a very small window anyway. It's the highest point in a small window or interval and the lowest point in a small window or interval. So let's begin. One of the theorems we saw in class was that an extrema, a relative extrema, only occurs at a critical number. But of course not all critical numbers will always give you a local extreme. So, to find critical numbers, that's the first place to start. Take our derivative. Here it's relatively hairless, as opposed to a hairy problem. Negative 4x cubed plus 4x. To find a critical number, set it equal to 0. Here you can factor a variety of ways. I'm going to factor out a 4x here. That makes it nice and pretty. That leaves us with x squared left-hand side. Actually, let's factor out a negative 4x. That'll make it even better. Negative 4x will give us negative times a positive will give us negative 4x, so x squared inside minus 1. So factoring out a negative 4x gives you negative 4x times the quantity x squared minus 1, which factors further into x minus 1 and x plus 1 as a difference of squares, or however you want to look at it. So here we have three possible critical numbers. Actually, three critical numbers, three possible extrema. X equals 0 from the first term, x equals 1 from the second term, and x equals negative 1 from the third term. So these are all of our critical numbers. They could be extremes, but until we use a number line as one method, we won't know for sure. So once you have your critical numbers, place them on a number line. So our x values here are negative 1, 0, and 1. And it's going to get messy in a bit, so we want to clearly show our intervals here with the little bunny hops. Again, these aren't mathematically necessary, but they may show you the intervals of increase and decrease. And we're going to investigate the behavior of f by finding values of f prime in these intervals. Okay, so this gets a little bit tough because we don't have obvious numbers to choose in some cases. So let's start with the easier ones at first. Let's start with plugging in a number into the first interval, which I'm going to start way out here, and plug in a number like, for example, 1,000. If you plug in 1,000, or 2, or 10, or anything in that part of the interval, you're going to get, plugging it in again into the derivative, which is right here, negative 4 times a gazillion is a negative number. A gazillion squared minus 1 is a positive number. And a negative times a positive is negative. And if f prime is negative, then f itself is decreasing in that interval. So the number line allows you to convey a lot of information in a very concise space. Likewise, let's find a value for the other end of our number line. For example, negative gazillion, or negative 1,000, or negative 2, or anything else that fits in there. So plugging that back into our first derivative, negative 4 times a negative number, a large negative number, will give you a positive number. A negative number squared will be a positive number, minus 1 will still be positive. So a positive times a positive will give you a positive result. And you can verify these by plugging in numbers that fit in those side of the intervals, but with a bit of reasoning you can figure out its polarity or its sign relatively straightforward. Now the hairy part. We have to fit numbers that fit in between negative 1 and 0, and 0 and 1. Well, this shouldn't be too hard though. 1/2 is probably a good choice. So f prime of 1/2, so that'll be right here. So that'll tell us about that little window or interval. Well, negative 4 times 1/2, and 1/2 squared minus 1. Well, we're not really concerned with what the value is, more its sign. So we can skip a couple of steps here to make it a little bit easier on ourselves. Negative 4 times 1/2 is negative 2, but more importantly it's a negative number. 1/2 squared minus 1, or 1/2 times another 1/2 is 1/4. minus 1 becomes a negative number again. And a negative times a negative will give you a positive. So in that window, we've created a positive result, which tells us that f is increasing there. Likewise, it was increasing here, and I forgot to mention that. And finally, we have our fourth part of our interval. An obvious test point here would be f of negative 1/2, but anything in that window should fit. Negative 1/3 or what have you. So plugging in negative 1/2, you get negative 4 times negative 1/2 times negative 1/2 quantity squared minus 1. Well, the outside here will give you a positive result, and the inside, negative 1/2 times itself, will give you a positive. Fraction minus 1 will give you a negative result, and a positive times a negative yields a negative. So that there is also a negative, giving you a decrease. So this one was a little bit longer than some of the other ones we've had, but the process is still the same. Find the critical numbers, place them on a number line, test values in your intervals created by the bunny hops, or whatever you want to call them, and the positivity or negativity of f prime will tell you the increasing or decreasing behavior of f. Fair enough. Well, we now need to use a bit of common sense and reasoning to figure out where we have local maximums and local minimums, or local maxima or minima, if you want to sound more sophisticated. Well, f prime being positive and then becoming negative and turning there at negative 1, well, if you go up and then you go down, you've achieved a maximum. So this change here is a maximum. Then you're continuing to go down, but at 0 things turn and begin to go up, which is the definition of a minimum. You never went any lower around 0 than you were before, and afterward you started to go in a positive direction. And a positive to negative change, likewise, would be another max. So these are the locations of our maxima and our minima. We still haven't justified it, though, because on the AP test, they do not accept a number line. Informative as it is, it doesn't quite show your reasoning. All you've done is plug in numbers and do some slight interpretation, but not much. So to actually justify where this thing has local extrema, we'll have to extrapolate from our number line in the following way. F has local or relative maxima at x equals negative 1 and x equals 1. Here comes the important word, because f prime changes from positive to negative. Dropped my pen, sorry about that. It's probably loud. Moreover, f has local minima, actually a local minimum in this case. F has a local minimum at x equals 0, because f prime changes sign from negative to positive. And there you go. An analytical method to find peaks and valleys of a function with a valid justification. One warning. A very common mistake in justifications is to confuse the positivity and negativity of f prime with the increasing and decreasing behavior of f. It is f that changes from increasing to decreasing if we go back to the previous slide. It is f whose increasing and decreasing behavior we have discovered information about using f prime. Whether f prime is increasing or decreasing would involve the second derivative and an investigation of concavity. So do note, incorrect answer would say f has a local maxima at x equals -1, x equals 1, yada yada yada, because this would be incorrect to say f prime changes from increasing to decreasing. We don't know how f prime changes yet. We only know that f prime changes sign from positive to negative. And we'll look at some graphical approaches about this to help you distinguish between the two possibilities later on in class. Okay, hope this helped.